All right, we are going to try and get this recording system to work so that I can talk to you about Grignard and organometallics and synthesis. So this is really all about what I like to call the alcohol disconnection. And so what that means is that anytime you have an alcohol, you by default have this piece of structure in your molecule. Now there may be an X group over here, a Y group over here, and a Z group over here, or they may all three be X's. In any case, you have an sp3 hybridized carbon with a hydroxyl group on it. So that means that you can imagine disconnecting retrosynthetically your alcohol into an organometallic X- and a carbonyl. Because what you see I'm doing here is I'm pushing back in my imagination. This is not reality land, this is retrosynthetic, how do I make this land? I am pushing that lone pair back in to generate the original carbonyl from whence this particular molecule could be made. Because if you think about it, what's happening here? What's happening mechanistically is my nucleophile X- is reacting with my electrophile, the carbonyl, to give you, in fact, that particular alcohol upon workup. So that's the alcohol disconnection, and what the take-home message is here is that you can do potentially do three different disconnections. The red one, the blue one where you'd add Z- to a carbonyl, or the orange one where you'd add Y- to a carbonyl. So the point of this mini lecture is to just go through a bunch of examples and show you how we can use this. So this will be our first alcohol that we'll look at. And because it's so much easier to see if you don't use line structure, I won't. Alright, so here is our important carbonyl-carbon. It's the carbon bearing the hydroxyl group. And what we can see straight away is we have three different groups. The nice methyl group, the H, and this whole big thing. It's called the benzyl group. So that means I ought to be able to find three different alcohol disconnections that would allow me to make this particular alcohol. So let's start with the blue disconnection. So if I, in my imagination on my scratch paper, push the lone pair back there and break this, taking that pair of electrons right there and giving them to that CH2, that means what I have done is generated the surrogate, if you will, for this organometallic nucleophile. And in addition, I am making the carbonyl. We're going to see there's always going to be a carbonyl with the alcohol disconnection. That's what you're adding your organometallic to. So what does that carbonyl look like? Well, the H is still on there and the CH3 is still on there. So if I look at this pair of reagents, I have a nucleophile and I have an electrophile, and in fact I should be able to react those together. That would give me the desired target molecule. Here's my target upon workup. So I make the alkoxide, the O-, and then it's protonated to give me that alcohol. So there is synthesis number one. Now, if we clean this up a little bit, what this really ends up being is the reaction between this particular real reagent, the Grignard, or it could be the organolithium, plus this aldehyde. and then H3O plus for my workup. So that's how we use the alcohol disconnection. All right, so let's look at our next example. Our next example would be, let's use the red disconnection. So what we're doing here is we are pushing, just a second here, pushing the electrons back to make our carbonyl, but this time we are taking this pair of electrons and giving them back to the hydrogen. So we are basically adding H minus, which of course is not a real reagent. What this means is we're going to add something like sodium borohydride, would be a reasonable choice. And what carbonyl would we add? Well, we would add, the blue group is still stuck on, that's our benzyl. Here is our carbonyl, and the green group is still stuck on, so we would add sodium borohydride, or maybe lithium aluminum hydride, to this carbonyl, and that will give me our target. So the last disconnection we'll do is the green one, and it's because we have 3 different groups attached to that. I'm going to spell it out. This is the carbonyl carbon right there. Because we have 3 different groups, the blue, the red, and the green, we have 3 perfectly good retrosynthetic disconnections. So what does the green one look like? Well, let's see. Now I'm going to push the lone pair back in and give that pair of electrons, break that bond, give that pair of electrons to the methyl group. So that means I'm going to be adding CH3 minus, which of course is not what we're really adding. We're going to add CH3 MgBr, the Grignard, or CH3Li. Those are the real reagents we'd use. And what would we add them to? Well, again, the blue group is still stuck on. And here's our carbonyl carbon. And what else stayed stuck on? Well, the hydrogen did. So we have 3 unique ways to make our target molecule. One, from the addition of this benzyl organometallic to acetaldehyde, or ethanal. One from the addition of NABH4, our nucleophile, to this particular ketone. And then the third one, the addition of a methyl organometallic to this aldehyde. So that is a ton of power for you when it comes to making alcohols. All right, let's do another example. How about we choose to make, I don't like that one. Let's do this guy. This looks like a great alcohol to me. So again, we're going to zoom in and focus on the carbon bearing the hydroxyl group. And we're going to redraw this so that we can see, clear as a bell, the 3 groups that are attached to this particular molecule. And I'm going to abbreviate, as you can see. One is an ethyl group, and one is a propyl group. And then the third one, of course, is the methyl group. So, since I have 3 different groups, I should be able to retrosynthetically disconnect these into 3 options. I can either kick out CH3 minus, or the propyl group minus, or the ethyl group minus. Now again, this is imaginary. These are not mechanisms. We are not really doing this in any kind of reality. I cannot break that carbon-carbon bond, not without mucho energy. This is just an exercise in helping me understand how I could make this molecule. So if we do green, our green turns out to be addition of this organometallic, or again the Grignard, to that particular ketone. If we do the red disconnection, that ends up being addition of this organometallic, or again the organolithium, to the C3C2 ketone. So I've got 2-pentanone, and I've got 3 hexanone. And now what about the blue possibility? So my blue disconnection, I'm kicking out the propyl group as an organometallic, plus a methyl ethyl ketone. So I have 3 different ketone starting materials, 3 different possible organometallics. All of them will react to give me, after workup, that particular alcohol. So the alcohol disconnection is great. Whenever you see an alcohol in any synthetic target from here on out, you definitely want to think about this, because you're using smaller bits and putting them together to make a bigger molecule. And what that translates into is value added. If you are trying to make molecules, say, for synthesizing materials for a solar photovoltaic or a new medicinal agent, that's what you're after. All right, one last example, and that is going to be to look at the synthesis of this primary alcohol. Now what you can see right away, and I'll make this quite clear by putting in the carbon, I have 2 groups here that are the same. So that automatically tells me there's only, in theory, going to be 2 possible retrosynthetic analyses based on the normal alcohol disconnection. So I punch these guys back in, and obviously, I hope, obviously, one of my possible routes is to just reduce that aldehyde. All right, clearly another possibility would be push those back in and kick out that guy. All right, so it is perfectly reasonable to think of synthesizing this Grignard reagent. And what would I add to that? Well, you remember the Grignard song. You add formaldehyde to get a primary alcohol. All right, so there are my 2 normal alcohol disconnections. But wait, there is one more, and it's the one that's always hard to see. It's the one that's hard to find, and it's really a little bit different because your electrophile is not going to be a carbonyl. In fact, it's a disconnection we've learned and known about for quite a while. I can, in fact, think about pushing my lone pair back in there, not to make a carbonyl, but to make an epoxide. So don't forget that one. If you push your lone pair over to the adjacent carbon, you can in fact do that same kind of chemistry. This plus this upon workup gives you that alcohol. And remember, again, we're talking about this being something like the organolithium or the Grignard. So I hope this has been a helpful mini lecture. We will certainly do plenty of practice problems using this concept, but keep that in mind. The alcohol disconnection really truly is your friend.